we're going to start things off today with a little experiment. For this one, you will need a bottle. Lid not required, but it can definitely work. You're going to fill the bottle up, about 2/3 of the way up. Then what you're going to do is you're going to take a Sharpie and you're going to mark where the water level is. Then we are going to place the bottle in the freezer and come back to it this afternoon. Now that we've started our experiment, let's take a little trip through the center of the Earth. Here we have the Earth. You can tell it's the Earth because that's Alaska. Anyway, we dive down, we drill down, we manage to get through to where no human has ever gone before. We get to the mantle, the outer mantle here, then we get to the inner mantle, and by the time we get here, the pressure is growing, and the temperature is rising, and everything is liquid, and we're swimming through in our amazing vehicle, and then we get down here to the core of our planet, and everything is still liquid. We go out with our sensors, we take a little teeny tiny piece of something, and we go, oh my goodness gracious, there are so many things down here. There's like iron and magnetism and all this other fun stuff, and we keep going until suddenly, boom, we run into the center of the Earth, the inner core itself. And we set our sensors, and we're like, okay, it's really hotter down here, there's a lot more pressure, but this thing in the center has the exact same composition as everything around it, but the only difference is it's hotter, but it's also solid. And those are the things that we're going to think about today as we learn all about solids. Earth, water, air, fire. These are the 4 classical elements in the Western tradition. But what if we called them by more modern names of solid, liquid, gas, and plasma?
States of matter.
Let me give you an example of what really makes something a solid. Pretend you're up here on top of a 10-story building. Here we have a nice person with a smile. And you decide that you're going to be not quite so nice person, and you're going to try throwing things off of the building. The first thing you want to try to do is you grab yourself a great big amount of gas, and then you blow it off the building. And it doesn't really go anywhere. It doesn't retain its shape. It's not like it has a form of your mouth. It just sort of goes. Then you decide to do the same thing with a liquid. So you grab a water bottle, and you unscrew the top, and you throw the water off of the building. The water will just sort of go everywhere. It will not keep the shape of the bottle. And then you decide to just throw the bottle itself off. You throw the bottle off the side of the building, assuming no one and nothing except for ground is underneath you. And what does and lands, but it keeps its shape. And you see, that is right there is the key part of what makes a solid a solid. What makes it different from a liquid and a gas is that given everything staying together, it will keep its same shape. But it's those givens that we're going to have to talk about next, because you see there are 2 of them. The first one is the temperature, and the second one is pressure.
Pressure running down on me like a copyright lawsuit if I keep singing this song.
But first off, we need to talk about what these 2 terms means. Let's start with temperature. Temperature for us is heat. Either it's hot or it's cold. But if we're really thinking about it in terms of states of matter, temperature is more a measurement of how much energy something has. The more energy it has, the more likely it is to be able to change form or change state from solid to liquid, etc., etc., etc. So in many ways, you could sort of see solid as being a lack of energy. And look around you and you can see that planet Earth is filled with many solid things. This is because we are relatively cold. If we were a lot closer to the sun, everything would just burn and die. But because of where we are, we get to be fine. And at where we are is also important because of the second thing that we're going to be talking about, which is pressure. Think of pressure as the amount of space that something has to move. So if you were to take a container and put a solid into it, and a liquid into it, what you would find is that the liquid would just slosh over everywhere while the solid would stay in one shape. But if you were to increase the pressure on the liquid so that it only had as much room to move around as the solid, if they are made of the same molecules / atoms, you will find that suddenly, because of the increased pressure, the liquid has kind of pretty much turned into a solid. However, we also know that temperature and pressure are very closely linked, and the higher the pressure something is, the higher the temperature as well. You can try this at home by pressing your hands together super hard and then putting them on a different part of your body. You'll find that the skin that you were pressing close together got hot really fast. So how do we then measure things on Earth? Well, what we do is we say to ourselves, let's hold one of those two things pretty much constant. Either we keep the temperature the exact same and increase the pressure, or we keep the pressure the exact same and increase the temperature. And we found that it's so much easier to increase the temperature while leaving the pressure the same, that is our default. Because you see, right now, you actually have a great deal of pressure pushing on you because of all these gases and small liquids around you that we call the atmosphere. For every single moment of your life, you have literally had an entire atmosphere's worth of pressure pushing down on you. How much is an atmosphere? Well, we have measured it in terms of pounds per square inch to be a little below 14.7 pounds per square inch. So if that's an inch, my face is 1, 2, 3, 4, 5 by 1, 2, 3, 4. About 5 by 4 square inches, which means that it's about 20 square inches, which means just on my face, there is currently about 293, maybe a little more, maybe a little less, basically close to 300 pounds of pressure shoving downwards every single second of every single day. And then if we were to just take a line of my head down, so that's 1, 2, 3, 4, 5, and 6, that is over 1,700 pounds of force from the top of my head and a line all the way down to my toes, pushing down on me constantly. Now remember, when we had that liquid and we shoved it into that shape, it pretty much became a solid. That is because the more pressure you have on something, the higher energy you need to break free of that pressure. Because that's pretty much what the phase transition is doing, is that it's changing. It has enough energy now that it can move around more inside of the pressure. Think about it in terms of having an energy drink while you're laying down on a couch. Pretty soon, you're not going to be able to lay down on a couch. You finally have the energy to be able to bounce around, or parents with coffee, or what have you. So if we do a fun little thought experiment, what if pressure was the thing that we were changing? Remember, as we're raising pressure, we're automatically raising temperature. That's just sort of how thermodynamics works. Because, well, the way the atoms jiggle around inside and just get excited bouncing off each other. If you had an infinite amount of pressure, you would also have an infinite amount of temperature, but there would be absolutely no room for anything to move around in. That means that you would have a solid, well, might actually be a plasmic solid? I don't know. Kind of fun if you think about it. That is infinitely warm. It will never ever change into a liquid or a gas. On the flip side, if you took pressure and lowered it to an absolute zero, temperature would also absolutely drop to zero. But not only that, but all these things on our planet that would always be solid will suddenly have no pressure. They'll have nothing shoving them into solids, so solids would be impossible, which is just so cool. Here's the other interesting thing, and this gets back to our question at the start of the show about why is the center of the Earth's core solid, but the area around it liquid, when they're made of the exact same thing, and that center is the higher temperature? It's because that center is under a much higher pressure. That center core is under a much higher pressure than the surrounding core area. Likewise here on Earth, because of how, well, I guess you could say little pressure we have, because there are plenty of places in our universe that have much higher pressure, there are certain elements that you will never be able to make solids of because it is physically impossible to get them cold enough, given the amount of pressure, to make them solidify. Now, let's go take a look at our experiment. If you look here, remember, we put that little line right at the top of the watermark where the water was just level with the bottom of it. Now, the ice has risen up here. But how does that make any sense if we just said that solids contract? Well, because ice is a very, very special solid where, given the strange circumstances that we live under on this planet, indeed on many places in our solar system, with a combination of temperature and pressure, ice does not arrange itself in the same way as everything else when it gets solid. Instead, ice expands as it gets solid. And that is an interesting inquiry, where if you're curious about the why, I'd recommend doing a little bit of experimentation and a little bit of research in why does ice get less dense when it gets solid, and what other kinds of water ice are there, and how do they form? So that's the end of the video on solids, my friends. Just remember that solids are a strange combination of temperature and pressure, where if you leave the temperature the same, in order to make a solid, all you have to do is change the pressure. And if you, like most of us, leave the pressure the same, because I don't really want to be adding more atmospheres, then it's the temperature you need to change in order to make solids. These two hold true for liquids and gases as well. Just liquids and gases get into the a little bit of a different territory. Next time, we will be exploring what happens when things get wet and how different densities of those things affect how they interact with each other. This has been another adventure with Gostentatious. If you like to tell your friends, if you hated to tell your enemies, and if you don't care either way, tell everyone. Thank you so much for watching. Please leave a comment below if there's a way that I can improve, and be amazing.